thing we're going to talk about in this chapter looks at the actual membrane components, not just what these lipids are. So you should be able to draw like individual lipids, whether it be a glycerophospholipid, a ceramide, a sphingomyelin with a ethanolamine head group. Get some practice with looking at those. But when we look at the lipid bilayer, remember, it's called a bilayer, so there's two layers actually when we look at these in terms of our cells and the membranes. Again, we have a nonpolar interior, and the outside or the inside of the cell are polar. That's where the head groups are oriented. Remember, these particular pieces, there's no covalent linkages between individual lipids, but they kind of aggregate together to put all the nonpolar stuff by one another and all the polar stuff by one another. Okay? So again, the overall lipid membrane is amphipathic. One side is polar, one area is polar, one side is nonpolar. So what this means, though, is if you have a signal or you have a molecule or a hormone or some sort of chemical that is polar, it can come close to the head groups, but it can't get through the membrane, which is why it's important that we have other species in our membranes to allow that communication into and out of that. So for example, sometimes what you might have is you might have other proteins or things like this that can let certain polar molecules all the way through the membrane. Okay, so we'll talk a little bit more about that once we get into protein structure. But again, the biggest thing about protein structure that you'll see in chapter 16 that I hope to remind you of is that structure dictates function. Okay, so, but going back to membranes, we talk about the membrane as what we call the fluid mosaic model. So the fluid comes from the fact that a membrane has a little bit of movement and fluidity to it. Too much movement is a bad thing. Too little movement is a bad thing. Okay, and that's going to relate to what we talk about when we talk about cholesterol. All right. The reason why it's called a mosaic, if you've ever taken an art class or have heard of the term mosaic before, and a mosaic, when you look at it from far away, you can see the entire piece of art and see a picture of a face or whatever it may be. But if you look up, it's made of individual tiles or things, so when you get close up, you can't see it. That's what we mean with the fluid mosaic model. Each of these individual lipids can move on its own. So it's fluid, and it's made up of these individual pieces to create the greater overall lipid membrane that we have. Okay? So again, those phospholipids, those glycolipids, so again, we say lipid because phospho and glycolipid could be both glycerol-based or sphingosine-based. These are the ones that we have there. In addition, though, to these lipids that are in there, we also have to have cholesterol. Cholesterol is there to help both stabilize and destabilize membranes. So if you remember back when we talked about fatty acids, we talked about saturated versus unsaturated fatty acids. Well, here's the thing. If you have a whole bunch of saturated fatty acids, like in butter, well, butter tends to, pack, and it tends to be a solid at room temperature. Could you imagine if our cells all of a sudden just form solids at room temperature? We would probably be dead, would not be good. So what happens is if we have a lot of saturated fatty acids, what happens is cholesterol comes in and sit in between those to help increase the fluidity of that membrane. Or that would basically cause it to be more fluid. Okay? So it helps to destabilize the membrane. Okay? So it destabilizes. However, here's the other thing. Cholesterol also stabilizes membranes. You're like, wait a second, how does this thing do two opposite things? Well, here's how. So let's say you have saturated fatty acids. They pack a little too tight. That's a little too much. But now let's say you have some other fatty acids that have a lot of double bonds, and that leads to these gigantic holes in your membrane. Well, that's also maybe too fluid. So what happens is cholesterol comes in there to help fill up those holes to help stabilize the membrane. So again, remember in a couple videos ago, I said cholesterol, too much cholesterol is a bad thing, okay? But too little cholesterol is also a bad thing. You need just enough to both stabilize and destabilize the membrane because there's a certain level of fluidity that you need in the membrane bilayer, and that's served by having cholesterol. So you can see, for example, in this picture from your book, you can see these little red things, are cholesterol to fill up the holes or to prevent these fatty acid tails from packing too efficiently. So that's how basically cholesterol helps to maintain the integrity of a membrane, maintain the level of fluidity, not too fluid, but not too rigid as well. So again, here's what the structure of cholesterol looks like. I do not expect you to draw it, but you should recognize it. Cholesterol is based on a steroid. So a steroid backbone are 4 fused rings, like you see up here, A, B, C, and D. Cholesterol, by definition having the OL group there, means that it has an alcohol group. So if you look at the overall structure of cholesterol here, you can see you have the 4 rings, but then we're just going to add a couple more derivatives, right? We're going to have the OH group for the OL, but then we're also going to have, again, some other groups going off. If you look at the total overall structure of cholesterol, with the exception of the OH group, the rest is all just carbons and hydrogens. So it is very nonpolar, which is how cholesterol can sit in the tails of our lipid bilayer. Now, if cholesterol had a lot more OH groups or amine groups or something like this, it would not be able to do that. So here's the other thing about cholesterol. It is a precursor for a lot of other species that we use in our bodies, such as vitamin D or steroid hormones like estrogen, testosterone, or bile salts and things like this. So you may have heard, and this just shows you from your book, maybe like cortisone or cortisone 10 or cortisone shots, things like this. This is actually a derivatization of cholesterol, or what we call the steroid hormone system. So you may have heard of cortisol. We talk about the cortisol levels in your stress hormones. So here you have cortisol. So you notice, again, 3 different rings that you have. Or maybe you've heard of prednisone, which is something that can be prescribed when people go onto steroids, right? Or cortisone. So a lot of these estrogens, androgens, these are all basically using cholesterol as a precursor. So not only do we use cholesterol in our membranes, we also use it as a precursor to a lot of these different communication signals that we need to get into different cells to say, hey, cell, go do this thing. So to get in and through the lipid bilayer to communicate to the cell to, for example, with estrogen and testosterone, to turn certain genes on and turn certain genes off with that communication. So if you take a look, though, oftentimes when we're looking at cholesterol, we hear about, oh no, you've got HDL and LDL, the bad and the good cholesterol. Well, that has to do with what we call LDL stands for low density lipoprotein. HDL, the good cholesterol, quote unquote, is high density lipoprotein. Now, cholesterol is very small and it's very nonpolar, which means it's not going to just go through your bloodstream on its own. So instead what we do is we package it in these lipoproteins. So it's a big giant basically ball of proteins and cholesterol and lipids. High density means there's a lot of stuff in it. Low density means there's not a lot. High density therefore is more efficient at bringing things around to your body and communicating and things like this. So high density, you have high triacylglycerols, which again, yes, there's energy fats, energy stores and things like this, but we also need them for communication and maybe using them for building blocks. But low density, right, has, again, we have low density and high density. High density we talk about as being good. We got less of those triacylglycerides and other lipids, so we have higher proteins for delivery. But again, too much of those fats just hanging out in your bloodstream, that's really not good. So this is just from your book that just shows you the lipoprotein combination if you've heard of these bad and good cholesterols before. Finally, we talk about lipids in the inflammatory response. So if you've ever heard of like inflammation, or if you've ever taken or seen somebody take things like ibuprofen, Advil, naproxen, these shut down what we call prostaglandins. Well, prostaglandins start from arachidonic acid. If you notice here, this is a fatty acid, and we have enzymes that will turn this into prostaglandins, which are an inflammatory and pain response in your body. So if you can shut down the enzyme that converts those, then you can stop your headache or your pain or whatever that may be, okay? So these non-steroidal anti-inflammatories or NSAIDs like Advil and things like this can help with those. So arachidonic acid can lead to pain and inflammation. So for some practice, maybe take a look at arachidonic acid and use your fatty acid nomenclature to name that. All right, if you have questions, please let me know.